Recording is rolling. Welcome to a new week, Monday, August 28th. So, yeah, you guys do have your labs out from last week. We're going to finish up a couple of graphs. You guys remember rolling those cars down those inclines? We need to finish analyzing that and make some conclusions. But before I get to that, we've got new alpha theta tutoring opportunity. So this is with Miss Walls, and Miss Rowe, this building downstairs. So do you love math? Question. Apply to Mu Alpha Theta, the Math Honor Society. Give back to the school by tutoring your peers in math and promoting the enjoyment of math. Questions, visit, and then there's these their rooms right here. 3123, 3120. Okay. So one thing I didn't tell you guys already is one of the best ways that you can learn anything is to teach it to someone else. Right? That's one way I got really good at math and physics myself is by tutoring other people, like this right here. Yeah, if that looks like an opportunity for you, got a class full of AP students. Some of you guys want to do, hey, maybe pick up some volunteer hours, maybe get count towards bright futures possibly, or something else you need. Right. Anyway, so that could be like a win-win opportunity right there. Trigonometry page. Most of you guys did turn this in when it was due back on Friday. No, it's one paper, it's two sides. I'm treating those as two separate assignments. If you did turn it in on time on Friday, then I already graded it. It's in the grade book from over the weekend. I haven't handed these back yet, so I'm still waiting a day or two for a couple late entries before I hand those back. But I know a couple of students may have been absent back on Friday. Anyway, get that in if you haven't yet. Wednesday, open house is scheduled on Wednesday. There's also a hurricane possibly scheduled Wednesday, 50-50, one or the other. We're going to see who wins. Homework pages. So back last week, you guys, AP, I gave you guys a couple of pages, right? One has these boxy type looking equations on it and some conceptual questions on the other side. These are all related to linear motion. In fact, the boxy type side has every basic category linear motion question that you could possibly have on it. Right? I also printed you guys some questions from the textbook, the college physics textbook. Does anybody not have either one of these yet? Right. Oh, okay, here. So one of each. There you go. All right, so I don't have quite a due date on those yet. I mean, I don't even know if we're going to be here Wednesday or what this week exactly is going to look like, but those are out floating around. Hopefully you're starting to read those, start to make sense of those. Okay. AP Classroom, that's been open a while. Again, there's a tentative due date. Probably going to move it back, but that's linear and projectiles is AP. You can see what kinds of questions AP is going to ask. Right? Okay, so that's been open. Right. Somebody knock my door. Nope, I'm going crazy. Okay, so today, I'm going to do a set of graphs with you guys that involves constant velocity. Then we're going to go finish that lab because we still got a couple of graphs to do. Now, those cars going down those inclines, that was an accelerating situation. So we're going to start with something more basic than that. Then we're going to go finish that lab. Then I want to derive some kinematic formulas with you guys that we can use to navigate this whole next couple of weeks. Okay? And then we'll go back and make some graphs like we're about to make, except for an accelerating situation. Okay? All right, so you guys good with the game plan? All right. Now, these first set of graphs we're going to do is just for your notes. You guys got your notes out? I know I said pull your labs out because we're going to get to those real soon. Okay? But first, for your notes. Okay. So notes right here. Here's the scenario. Let's have a car drives at constant velocity. Now, you guys know constant velocity. That means that what's constant and what else is also constant. The what and the what. Two aspects of velocity. Speed and also direction. Boom, boom, and boom. All right. How do you nail on that? Speed and direction, right? That's what velocity is, right? Speed, but also direction. Right? So if it's constant velocity, not only does the speedometer stay the same, but you're also not turning the steering wheel, right? We're not going to talk about steering wheel for a few weeks anyway, right? But draw three sets of axes. Three sets of axes. Let's say this is just we're on I-95 going straight north towards Jacksonville. Right, you guys can imagine that, right? Just cruise control. Right? Trees flying by, constant. Right, so let's go how far in meters, x in meters, as a function of time and seconds. We're going to go how fast in meters per second as a function of time and seconds. And we're going to go acceleration in meters per second squared as a function of time and seconds. Right? Now, a reminder from last week, I know I introduced some of these concepts from last week. Do you guys remember what is acceleration? Acceleration is a rate change of what? The velocity. Yeah, so if you have a changing velocity. actually here, let me flash this poster up here, this definition. So acceleration is a rate change of velocity, right? So if you're slamming on the gas pedal and speeding up, or for that matter, slowing down, you could go that way too. If you have a difference in velocity, like final minus initial velocity, right? And then there's some rate that's happening. So I'm dividing by a time interval. That's what delta t is, right? Like change in time interval. Sometimes I'll just write t for time, right? Okay, you guys get that, right? There's a different kind of acceleration called centripetal acceleration that involves the steering wheel. That's this guy down here. Don't worry about this guy yet, at least not for a few weeks. In a few weeks, this guy's going to come back. But right now, we really care about this top area. Okay, so you guys know displacement, like how far, velocity, how fast, and acceleration is the rate change of how fast. Okay? And the scenario is, well, this right here. Car drives constant velocity. So north on 995. Right, you guys go ahead and draw those 3 graphs. I'm going to walk around class and see who gets those right before I give you guys the answers. And find out who my winners are. All right, so I got 3 graphs. Let's see how you guys are doing here. Okay, some of you guys are still taking the axes. That's all right. But does it look right here? Okay. Oh, yeah, it's kind of. Well, I didn't realize that. Which is kind of annoying. It says car drives at constant velocity. That's hard. Car drives at constant velocity. All right. See how you guys are doing. Okay, you guys got your axes. That's good. Okay. For it. All right. Okay, that one right there looks good. All right, Sarah's got the x versus t. All right, I think Sohan's got x versus t. Great. All right, Ian figured out x versus t. Max figured out x versus t. Ooh, so a lot of x versus t winners. All right. I might be missing a few winners. I don't know. Okay. If I missed you, sorry. Oh yeah, Hadley got x versus t. Ooh, Melissa figured out v versus t. All right, Sydney's got x versus t. Catherine's got x versus t. All right. Okay, so a lot of you guys are getting x versus t, and I got one of you guys figured out v versus t. So let's put this together. Okay. Actually, what I'm going to do is these 3 sets of graphs. What you guys will see is I can just swap out the story, and I'll analyze any particular motion story in terms of these 3 sets of graphs. Okay, so this is going to be a common setup, right? And what I'll usually do is start with the middle graph, v versus t, and then branch out from there, right? Because these 3 graphs are connected, but maybe I'm getting a little ahead of myself. Okay? So let's say we're driving north on I-95. At some time we start measuring, it's like, hey, we got like 70 miles an hour, right? Guys, 1 hour later, how fast are we going? Constant velocity, 70 miles an hour. The next hour, how fast are we going? 70 miles an hour. How about 1 hour later? 70 miles an hour. Hey, constant velocity. That means velocity is constant. Look at there. That's a flat line on v versus t, right? That's telling you what your speedometer needle is reading. Okay. Well, I said miles per hour. I know my units are meters per second and seconds. Okay. Miles per hour, meters per second. You guys get it. It's the same graph shape, right? You just swap out the units. You guys get the idea, right? Right. All right. And a lot of you guys also figured out what displacement versus time looks like. And what did you guys draw? Yep. Boom. There you go. Direct relationship, linear. Actually, you can start wherever you want. Most of you guys did what I was going to do anyway. You said, well, at time 0, let's just call it 0 displacement. Although you technically don't have to, right? But yeah, I like to do that too. Right? Well, you could shift the whole thing up, and that would also be possible, right? All right. So okay. So that can make sense, right? Like after 1 hour, maybe you move like 70 miles, and after the next hour, now you're up to 140 miles, and then the third hour, now we're like 210 miles, right? So we're like gaining 70 miles every hour. Right? Swap it out with meters and seconds, and same idea, right? Okay. All right. Now, who figured out the third graph? What does the third graph look like? Who can tell me? What you guys see?
Flat line at 0.
Flat line at 0. How'd you know it was a flat line at 0? Yeah, because there's no acceleration. That's what constant velocity is. Guys, constant velocity means there's no acceleration, right? If you want the more formulaic version, right? Final velocity and initial velocity would be the same, wouldn't they? Because it's just cruise control. These 2 guys are the same, right? Beginning and end of an interval, right? This isn't changed. This whole numerator is 0. Maybe like a couple hours has passed, whatever. 0 divided by anything, 0 acceleration. Right? Hey, cruise control, constant velocity in a car. Would you feel a lot like you feel just sitting in your seat right now? Yeah. Maybe you're rumbling around a little bit, but yeah, right? Are we on a giant spinning planet moving about 1,000 miles an hour? Yeah. Can you feel that? Nope. Right. That's this too. 0 meters per second squared. Boom. You guys okay with those three graphs pair with that story, right? This story here, these three graphs, same thing. They describe each other, right? Now, what I want you guys to see before I move on to the lab and get my way towards that, right, is that there are relationships between, or among, I guess, these three graphs, right? Like, if you have one graph down, you can pretty well figure out what the other two look like. Okay? Here's what I mean. Let's start back where I started here with velocity versus time, right? Wait. Yeah, but wait, let's do it. Okay. So velocity versus time. Remember, I've been flashing up this definition of linear acceleration is the rate change of velocity. Well, if rate change of velocity, what property is that on a graph? The rate change of something. It's not a coordinate. It's a slope. Slope. Yeah, the slope is the instantaneous rate change, right? Hey, guys, what is the slope of this line? 0. 0 rise over run. Right? And that also has units, right? Like rise over run. I know it's like 0 rise, 0 meters per second per passing second. That could be called meters per second squared, right? It's still 0, right? But what I'm trying to get at is that the slope of your v versus t graph tells you the coordinate of acceleration versus time, which in this case happens to be 0, right? We're starting out with a pretty simple case, just constant velocity, right? Right? But more generally, that'll be true when these graphs get a little bit more fun. Okay, right? Guys, get that? The slope of v versus t tells you the coordinate of a versus t. Right? Hey, if you look at these units all the way down, meters per second per passing second. Ooh, do you think that the same pattern is going to apply from x to v as from v to a? Huh? Let's see. Like if you're going like 70 miles per hour, every hour you pick up another 70 miles, another hour 70 miles, another hour 70 miles. Wouldn't the rise over run here be like 70 miles per every hour, right? Which would describe your speed, wouldn't it? Oh, you guys think the slope of x versus t tells you the coordinates of v versus t? Huh? It's looking like it does, right? We swap out with meters per second, but it's the same idea, right? Pick up like go 5 meters in the first second, then 5 meters, and 5 meters. Looks like you're picking up 5 meters per second. You know, put a 5 right here, right? Just get that? Okay. Now that's going from top to bottom. The rate change of x versus t tells you v versus t. The rate change of v versus t tells you a versus t. Right? That's like slope information. Do you think you can also go from bottom to top, like somehow? Right? But let's go from v back to x. That's what property. I bet some of you guys can figure this out. What property of the velocity versus time graph do you think could tell you something about your change in displacement? What property? Let's see. Probably not the coordinate, not the slope, because that's the other way. What else are we looking at a graph? If it's not a coordinate, it's not a slope. And ooh, good guess. Or something else. Right. How about this? Let's look at the units. Because if you guys can figure this out before I tell you what it is, then that's better for your brain. We're trying to get some number of meters. Like we're changing some number of meters, right? Okay. And I have to somehow get that from like meters per second and seconds. Guys, what can you do to meters per second and seconds to somehow get meters? What do you do to these two units? Multiply them, exactly. It's like seconds over 1. Maybe meters. Now, if you're looking on a graph and you're multiplying these two units, that tells you what property of this graph. An area. Bam, an area. It's like if you go like 70 miles an hour for an hour, how much you moved? 70 miles. And then the next hour, you pick up another 70 miles. And then the next hour, you pick up another 70 miles again, right? That's like a displacement. Hey, that's like v times t. Maybe I have some v here, some constant velocity times time. Is velocity times time like a change in displacement? Sure is. That's an area relationship. The area under v versus t tells you the change in your location, the change in your displacement, right? Now, again, you don't necessarily have to start at 0.0 here. You could go like up here, down here, okay? But it tells you a change. Okay? Do you guys think the same exact pattern is going to apply going from A to V? Right? Like, ooh, what is the area of that skinny right there? What's the area of this rectangle? Yeah, 0, right? Okay, there is no area, right? It's flat, like a pancake. So if you're like adding up the area, you're not adding up anything, which means the change in velocity over some time is what? 0. So whatever speed you start with, it just doesn't change. Hey, what if the car's going really slow? What if the car's going really fast? Does the specific speed matter? No, you can be going really fast. Oh, if you're not accelerating, then I mean, we're going like 1,000 miles an hour right now. Let's spin a plane. Yeah, it's the same pattern, right? So the area under A versus T, like the accumulated area, tells you the change in velocity, right? So you guys can navigate back and forth. Right? So a lot of times I like to start with V versus T because this is a very information-rich graph. If you know what V versus T looks like, that's one step away from X versus T. And that's the other step away from A versus T. Okay, see that? You can go back and forth, up and down. Okay. You guys got that concept? Okay. All right. All right. So this is for a constant velocity situation. By the end of class, we'll do an accelerating situation. But before we are able to quite tackle that, we still got a little bit of your lab left where we can actually derive the equations that would lead you to like that type of outcome. And so let's do a quick review, and then we'll get back to where the bell rang back on Friday. So I split you guys up into 4 experimental groups. You guys were rolling cars down inclines. Some of you guys were changing out the mass, and you said you realized, oh, there's the mass of the car didn't actually affect its motion at all, right? So in the formulas this week and next week, mass is not part of any of these formulas. Right? Now in the future, it'll be part of other formulas, but you won't really see mass this week or next week, right? Let me skip that one. Come back to it. Right. Some of you guys did V versus T, so you're saying like different times. What speed does it pick up to? And we were getting a linear relationship, and we identified the slope. In this case, it was 73 centimeters per second squared. Guys, that number right there, that property of that graph, 73 centimeters per second squared, represents what physical property? Not displacement. Acceleration. See this equation we crafted back on Friday, right? The speed it picks up to is the rate changing velocity times however much time it's had to pick up speed, right? It's going 1 second. Now it's going 73 centimeters per second. 2 seconds, 100 and maybe 50 almost centimeters, right? You guys get that? Right? No. Direct relationship, right? Some of you guys did X versus T. We made a pair of graphs for that. Now, X versus T ended up being a parabola type situation, or at least we were suspecting it was a parabola. Spoiler alert, it is. So if you suspect that, I introduced you guys this linearization tool. Actually, I was going to do that with a circle activity that we never got to, but maybe somebody else put that in. Right? So if you suspect that X is proportional to T squared, you can actually graph X versus T squared. Notice that these two axes are different. The one on the left is time in seconds. The one on the right is time squared in square seconds, right? And then that actually lined up in a straight line. Now, know this linearization technique because you're going to see it all over in AP. AP loves graphs. AP loves linearization. I think it's pretty cool too because you can very quickly whip off a graph, right? And now we have how far the car is rolled is proportional to the time squared, right? And then we got a number with some units on it. So if it's rolling 1 second, about 24 centimeters. 2 seconds, 2 squared is 4. That's almost 100 centimeters, right? Is that right? And finally, we got one set of graphs we're about to do. Right, so you guys got your data out? Ready to put this together? Right, I think these tables over here, we're doing V versus X. Right, so who wants to volunteer their data? Was somebody about to do it back on Friday? Right. How about, I'm going to pull somebody. How about Sarah, you got some data? All right, you got V versus X. So what's one of your coordinates for V versus X?
So we got the map when the distance was 220 centimeters.
All right.
The speed was 1.27.
All right, so 220 centimeters. Right here. And you said 1.47. Ooh, okay. I got the. I think I'll just be able to fit this. Yeah, it's right at the top of the page. Okay, looks like I scaled this differently back on Friday, but this will just fit on my page. Just have to extend that a bit. That's like right there. Bam, just barely fit. Okay, what else you got?
What next? When it was 170 centimeters, it was 1.29.
170 centimeters, 1.29, 1.2 is right there, 1.29. Okay, that's probably pretty close right there. All right, what else you got?
Next one was 120 centimeters, it was 1.07.
120 centimeters, 1.07. It's just right about there. Bam.
When it was 70 centimeters, it was 0.81.
70 centimeters, 0.81. Bam.
And when it was 20 centimeters, it was 0.4.
0.43. Okay, 20 centimeters, 0.43. It's right about there. Bam. Look at that. Right. Okay. And where's my graphical relationships? Right. So that data right there, that's right about what we're looking for. Which of those graphs is that going to be? How about root? Right. Maybe linear could be a close candidate for second, but I'll show you guys why it's not linear. Right? If you assume linear, I mean, sometimes it's hard to distinguish between linear and parabola or linear and a root. Right? If you assume linear, it looks kind of close, right? Wouldn't it have a huge y-intercept? Now think about what that y-intercept would be. That'd be as soon as you let go of the car, it immediately has a velocity, which isn't true, right? Isn't it true that you release cars from rest? So position 0 had 0 velocity. So this is kind of a coordinate 2, or it would have to be logically, right? 0, 0, right? Otherwise, unless you give the car a push. If you gave the car a push, then in that case, maybe it would have some kind of intercept. But if you release it from rest, this has to be a point on the graph. So that's like more a hint that it's probably going to kind of curve down like this, which looks exactly like what's going on, kind of bends down like that. I see that? Okay. Now, suppose I suspect a square root. I'm going to say I suspect b squared is proportional to x. Right? I meant to say this. I'm going to say v is proportional to the square root of x. But if you get one, you can get the other, right? You just square both sides. Isn't that true? I meant to write this first and then this, but you guys see it's the same thing, right? Right? Okay. Right. How can you confirm that? Well, we'll do it the same way we did with x versus t. Right? So this time, though, I'm going to square the v's. So I'm going to do v squared and meters squared per second squared as a function of distance in meters. Distance in meters. Well, right. Now, distance in meters, let me just go ahead and leave the same, scaled up to 20. Let's try that. 1 meter, 2 meter, 0, 1, 2, 3. How about that? Okay, that should fit all the data. All right. Okay, so Sarah, did you have the squared values of all your v's? All right, good deal. What's your largest v squared value?
3.1.
2.16. Okay, that looks about right. Yeah, let's go. 1, 2, 5, 0, 1, 2, 2.5. Okay, 2.16. Okay, and that was a 2.4 meters.
220.
Or 220. Yeah, you're right. 2.2 meters, 220 centimeters. Yeah, that's what it was. Okay. So at 220 centimeters, it was. Sorry, can you tell me that again? It was 2 point what?
2.16.
2.16 meters per second. Let me go ahead and throw that coordinate on the board. All right. What was another coordinate on this graph?
It was 1.66 at 170.
1.66 at 170. Ooh, that's right about there. Bam. All right, what else you got?
At 120 centimeters, it was 1.14.
120 centimeters, 1.14 meter. Wait, oh, sorry, 120 centimeters.
Yeah, sorry.
Okay, yeah.
120 centimeters, it was
1.14. Yeah, that looks right about there. All right.
At 70 centimeters, it was 0.63.
70 centimeters, 0.63, right about there. Bam.
And then at 20, it was 0.18.
20 centimeters, 0.18. Bam, right there. You guys see how those points pretty well lie on a straight line? Look at there, Z's. Look at that. Look at that. Now that is a direct relationship. So yeah, the square of the speed is directly proportional to x, which is what I was suspecting that would lead me to that anyway, right? You also see lots of parabolas and roots in this class. So sometimes you square one variable, it should line up in a straight line. And then the advantage of that is, see, you can grab a line of best fit by getting the slope. Just do like y equals mx kind of deal, right? So I'm going to play off this coordinate and say there's a straight line between that coordinate and the origin, just to simplify this a little bit. I mean, that would probably be pretty close. Like rise over run. Can I do rise over run between 0, 0 and this point that I listed? The rise is 2.16. Oh, I put meters per second, but that's not even true. It's meters squared per second squared. That's what I meant to do. Okay, right. Divided by, and then 220 centimeters, I'll call it 2.2 meters just to have meters and meters consistent, right? Call it 2.2 meters, right? 2.2 meters. Right. So the rise over run, I'm getting 0.98 1/8, blah, blah, blah. Okay, that's plenty of precision right there. And the unit would be, well, guys, what is meters squared per second squared all divided by meters? What is that? Meters per second squared. So this 0.98 has units, and it's in meters per second squared. Is that, which looks like a what kind of unit? What kind of unit is measured in meters per second squared? Acceleration, right? Okay, right. Now, I'll tell you what though, the slope of this line isn't exactly the acceleration. It is a multiple of the acceleration. It's off by a factor of 2, right? Or is it v versus t? That was the acceleration. Right? This one's off by a factor of 2. Right? Anyway, so and you guys had different cars that rolled a little bit differently too, so that's all right. Okay. Well, let's craft an equation for this one. Here's v squared versus x. I meant to put that title. Right? Let's get an equation. Isn't v squared equal to 0.98 meters per second squared times the rolling distance x, right? So now, if you want to know how fast it went as a function of how far it rolled, you can plug in any distance you want. Let's say 1 meter. Car rolled 1 meter. How fast is it going? Well, 1 meter times 0.98 meters per second squared, and then take the square root, and bam, that's how fast. Okay. You guys got that? Are we good? Any question? All right, so one last thing with this lab is the lab write-up. Now here's what we're going to do with the lab write-up. We're going to save that part for tomorrow. I'm going to give you guys these rubrics. I'll show you the rubric now so you know what to look for by tomorrow. I'm going to give you guys a colored pencil, have you grade yourself so you know exactly what to look for. I tried to make this as close as I could to an AP style write-up. It's 12 points. AP has 12-point write-ups exactly for this part. Okay. I'll show you one of them today just so you know kind of what it looks like. What's the relationship between mass and time for a car rolling down an incline? I think it was this team over here, mass and time, right? So I got the question, AP would give you a question, right? So look for measuring tools. You need a scale or triple beam balance. You can get masses. Put meter stick, put a stopwatch or a timer, put a protractor. Now the meter stick just so you can establish a set distance, and protractor so you can at least get the angle, right? So just so you have set up, right? Data gathering procedure. And look for each of these measuring tools has to be mentioned one at a time in your procedure. The first step is set up an incline at a shallow angle above the horizontal for a toy car to roll down. Bam! That is the entire setup right there, isn't it? Just look, it's all in one sentence. Sometimes you need 2 sentences. That's okay, right? But look, it's just a very brief description of exactly the setup. That's usually worth the point itself. I didn't make it a point just because I'm trying to get the points to add up to 12, right? Use a protractor to measure the incline. Bam! 1 point for mentioning the use of the protractor. Use the triple beam balance. Bam, a point for mentioning triple beam balance. Use the meter stick to establish a 200 centimeter fixed distance. Now, not everybody had this fixed distance, but you guys would have over here, right? So bam, that's a point. Use the stopwatch to measure how much time. Bam, there's a point for application stopwatch. Set this up 2 more times and take an average. So you guys remember 3 times take an average? Bam, that's always a point in this particular FRQ. That's always going to be a point. Do it 3 times so that you can reduce random error. In fact, you probably want to write that out when you get to the upper cube. Okay. Attach a small lab weight to the car, repeat steps 3 through 6, do this for 5 different car masses. So you've established the independent variable. That might be a point. Your data is graph M versus T, and then the conclusion is that there's no relationship between M and T. Right? That's only one of the 4 parts. I'll give you guys the rubrics tomorrow so you can, within your own groups, because there's 4 different rubrics going on around, and I got limited class time, right? So we're gonna say that tomorrow. Can you guys save your labs for tomorrow? Right, everybody's got your data and everybody's got all the graphs, all 6 graphs. Everybody's got all 6 graphs, right? All right, let's move on to what do we got next? So we finished the lab. All right, let's derive some kinematic formulas. You guys ready to derive some kinematic formulas? And the one I'm going to use is this V versus T right here, exactly from your lab. See that V versus T, that straight line relationship? All right, you guys ready? You guys ready? All right, so this is good notes right here. If you're taking notes, it's a bit more active than watching. It's good for your brain. I'm going to do a side-by-side setup. Let's do a couple of V versus T graphs I want to look at. One is just straight from your lab. So V versus T. This one's straight from your lab. Got velocity in meters per second, time in seconds. Okay. And let's just have a straight line relationship just like this. Okay. Okay. Now, we already got that the acceleration of this is the acceleration is the slope of that curve, right? You guys already got that? Right. That's the same thing as this, right? Change of velocity per change in time, acceleration, same thing as the slope of that. Okay, so we figured that out. That's okay, right? You guys got that? Rate change of velocity is acceleration. But a few minutes ago when we were looking at the constant velocity, do you guys remember what property of this graph tells you how far it rolled? The area. You guys remember that? The area under v versus t tells you x versus t. Right. Later on, as the year goes on, it'd be so much, I think, look, different axes with different units, but you can figure it out, because in this case, area of a rectangle is like base times height. Guess what is meters per second times seconds? Or I asked that before. It's meters, right? So if you look at what the units are doing in terms of the slopes of the area, it can tell you what physical property that represents, right? So let's see, it works for a car at constant velocity, but what about this accelerating car situation? Accelerating car, let's find out, right? Ooh, do you guys see like a triangle type shape? Okay, because maybe the first small interval time it went picked up to that speed, the next small interval time that speed. So like the speed's constantly changing. And look at all these slivers here. All these slivers are like tiny or like skinny rectangles. Well, not exactly rectangles, they're like trapezoids, but they're approximately rectangles. Okay, so they each represent like a tiny distance the car moves, and then it accumulates. You see it? All right, now let's put this all together. Suppose the car was going for some time period t, and I'll just call this entire interval t. Is that okay? The base is t. Base of that triangle is some unit t long in seconds. Okay. Now it's picked up to some final velocity, and that final velocity, what is that final velocity in terms of this time and this acceleration? What times what? Acceleration times time, a times t. Wouldn't that be the final speed picks up to if it started from rest, which this one is, right? Is that true? Right? Do you think you guys can solve for the area of that triangle in terms of just acceleration and time? Let's try it out. So area of a triangle, and you guys know it's going to represent displacement, right? X is displacement. What is the area of a triangle in general? 1/2 times base height. Yeah, 1/2 base height, right? So I got 1/2. I got the base, which is equal to some general time t, and I got a height, which is equal to a times t, right? Hey, that time, so at the same time? Ooh, so ooh, I can push those together. I can call this what? X equals what? 1/2 a t squared. Look at you guys go. Right. I was gonna, here, okay. There are different ways to derive this. I like the graphical version. Okay, you guys get that? Okay. That sure does remind me of your guys' lab. You guys remember x is proportional to t squared, right? And the slope looked like it had acceleration units, but actually it's half the acceleration. Ah, look at that. 1/2 a was equal to the slope of that graph that you guys made for your lab. You guys see that? Look at that, right? Okay, now let's do another v versus t. You guys okay so far? Any questions so far? This is all checking out? Okay. But I want to make a change. What if instead of releasing the car from rest, what if you gave it a push, right? Or what if instead of like dropping the ball from an edge cliff, what if you chuck it straight down, right? So that at time 0, it's already in motion with some initial velocity v naught, right? So I'm still doing time in seconds on this axis. I'm still doing velocity in meters per second on this axis, right? Okay, you guys get that? Okay. Oh, reminder. Lots of symbols you guys are seeing thrown out around. Remind you guys remember very first day of school, you guys got this page, among other pages. So here's variables and units, and we're just dealing with these right here. So t, time, measured in seconds, v, velocity, meters per second. V naught, like, is initial velocity. V sub f is final velocity. A is acceleration, and lowercase g is acceleration due to gravity, like free fall acceleration, like free fall. That is acceleration, it's just due to gravity, okay? So when you guys see those, is that all right? So initial velocity. What do you guys think the rest of this graph looks like? Hey, if it starts with an initial velocity, isn't that just identical to starting from rest, except you just started keeping track of it like right about there, right? Could you just take this and copy paste it right here? Does it have the same slope? Yeah. It's just like, yeah, I just take my ruler, parallel, slide over, point. I got myself that graph. Just looks like that. It's the same slope. It's the same acceleration. I mean, you know, given the same ramp angle, the same gravity field, whole thing, right? Or if you're at the edge of a cliff and you like chuck a ball straight down, like, throw it straight down. As soon as you leave your hand, it's still under the influence of gravity, it's still picking up at the same rate. The acceleration doesn't change, right? Now, if you want to say how far did it go, like how far did your car roll? How far does the ball go down like the cliff as a function of time? Do you think it's the area of that there trapezoid? Can you guys split up the trapezoid into a triangle sitting on top of a rectangle? You guys do that? Right? area under the curve. We're trying to figure out x. How far did the car roll? How far did it move? Right? Okay. So we got v versus t. After a certain amount of time, you can know how fast it's going just by picking up the coordinate. You can know the acceleration by the slope, which is the same as before. Right? Right? And now we want to say, how far did it go? Well, before it was the area under the curve, so it's probably also the area under the curve for this one. Right? Right? Ooh, this triangle right here, isn't it just 1/2 at squared, just like before? 1/2 at squared, right? But what about this rectangle? What about this rectangle right here? What's the v naught times t? There you go. Whatever your initial speed was times the time is the area of that rectangle. So what's the total distance moved? Can you just tag those two together? X equals. Oh, whoops! I'm so sorry. I meant there's always a certain way I write this. I meant to write it this way: v naught t plus 1/2 at squared. Guys see right there? That right there? Right? Ah, so the simple version is on the left if it starts from rest. This is at v naught equals 0 meters per second. But the one we just did on the right is a more generalized version. So if you like throw it down or give it a push, right? Right, guys get that? Right, everybody right so far? Right. Any questions? Right, so let me show you guys some different perspectives on these things here. Right, let's do this one right here. This one right here. Right. So these 3 kinematic formulas. There's a poster hanging in my room here. This one has the training wheels on it because it's got the units written underneath it. So, right. But here, this middle one. The velocity picked up to is your initial velocity plus acceleration times time. That looks like y equals mx plus b. That's kind of what we just did right here. This pink line. Right. Right. Or if you like, you could rearrange this and get acceleration is looks like this right here and this right here, the same thing, just a few algebra steps away from each other. You guys see that? Maybe delta t some time interval. I could just call it t. It would look like this, right there, right? Then look at this top one. Hey, this top one is just what we did. We said how far it goes on a v versus t graph is this rectangle plus this triangle. That's what we just derived. You guys see that? Right. Now, if you look at those top 2 formulas, right, for kinematic motion, right? Let's see what we got. We got different, right, like how far x. You know what I made you do first? Right. Let me show you guys a little bit different perspective before I make that point. Okay. Right. If you're keeping track of how many variables we're juggling, we're only juggling these 5 variables right here. It's just these 5 variables. Right? How much time is going? Right. What's the initial velocity? What's the final velocity? So velocity at the beginning of an interval, velocity at the end of the interval. Right? How far did it go? Right. And if the velocity is changing, then what rate is it changing? That's acceleration, right? There's only those 5 variables. Right? We're just juggling those. Right? And in fact, if you can ever identify any 3 within a problem, then the other 2 become locked in place. They become solvable. Right? Right. All right. Right. So that's another perspective right there. Right? So let's go back here. Right? So these top 2 formulas, they do have some things in common. They possibly have an initial velocity going on. They possibly have some time taken. They possibly both have an acceleration, maybe. Right? By the way, what if acceleration is 0? What does this bottom one become? What does this middle one become? Oh, if acceleration is 0, this piece goes away, right? I see. Final equals initial velocity. Right? If there's no acceleration, there's no change in velocity. Okay, so that's at least consistent, right? What about this top one? If there's no acceleration, oh, it just boils down to that right there. Distance equals speed times time. If acceleration is 0, this piece goes away, right? You guys see that? So if you're driving towards Jacksonville and you see a sign on the side of the road that says Jacksonville, 140 miles away, you're going 70 miles an hour. Okay, 70 miles an hour to go 140 miles. How long does that take? Like 2 hours? Okay, that's a 0 acceleration. That's like the first set of graphs we just put together, right? Okay, you guys see that? Okay. Right. But what if I threw a question at you guys that I did not tell you the time interval, or I did not ask for it? Like you guys see time as part of both of these, right? I'll give you guys an example. You're in a car, right? You're just driving along, and suddenly a deer runs out in front of you. You slam the brakes. It takes some distance for the car to roll to a stop. Right? And I want to know, how much road do you need to come to a stop? Well, guys, roll to a stop. Already there's an implied value there. What do you know about final velocity for roll to a stop? 0, right? Maybe you look at your speedometer and you know how fast the car was initially going. So you know this, and something about the property of the tires in the road tells you the rate you can slow down. Do you guys think if the road is wet, that you're not going to slow down as fast? You probably need more road, right? Okay, so some property has to do with acceleration. We'll talk about in a few weeks, right? But what you have and what you want to know notice I never told you how much time it would take for a car to roll stop, and I didn't ask you. Now, you could solve for t first, and then using this equation, and then plug the t up in here, and then figure out the stopping distance, right? But there's maybe like a faster way to do it, and that's where I'm introducing this third equation right here. Notice this third one doesn't mention time passing, right? Not because there isn't time taking in background, there is, right? But it's a quick way to get the answer maybe for that situation I just gave you. Right? You look at the speedometer, right? You're going, oh, I'm going so many miles an hour, right? And then deer jumps out in front of you. I got to brake to a stop. Send this guy to 0. And I know the rate the car can slow down because something about the tires and whether it rained or not on the road, right? Then you can very quickly solve for x. That's the braking distance. You guys see that? Okay. So depending on what variables you have, right, ideally you should be able to identify 3. Sometimes one's implied, right? Like if someone says drop something or release from rest, okay, initial velocity 0 meters per second, right? Okay, so something like that. Right. But ideally you should be able to identify 3 so you can solve whatever you need. Okay. So system equations between the first 2, we'll get to the third one. I'm not going to drive that in class, but if you're really curious, you might go home and check it. Go ahead, substitute out the t here, and you'll get the third equation. Okay. All right, everybody good so far? We're good? All right, we're doing all right. I know it's a tight fit, but we're going to fit in this last set of graphs right here, constant acceleration. Right, you guys ready for constant acceleration graphs? You guys ready for your notes? Let's go back to your notes. We're going to do a constant acceleration scenario. Oh, constant acceleration. That is like the car in incline lab, right? Except we're going to do a speed up version of that. We're going to go drop a ball. Here's the scenario. Drop a ball from the edge of a cliff, right? You guys got that? Drop the ball from the edge of a cliff, right? Which is pretty much identical to letting your Hot Wheels car rolling down the incline. It's just greater acceleration. That's really the only difference, right? I'm going to define down as the positive direction, just because it's moving down, gravity's pulling down, right? You don't have to do that, but all the numbers will be positive, so it's probably more intuitive, right? We're going to ignore air drag. Okay. Ooh, guys, if suppose you're trying to make sense of the situation, you drop a ball from the edge of a cliff, and you think, I think I might be missing some information, right? What do you think? What gravity field do you think you're supposed to normally assume as a default? Earth gravity, right? So can we say G equals, right? Now, maybe I'll say assume, right? A lot of times that's a common assumption in this class. If they don't tell you what planet you're on, free fall, probably on Earth, right? Does anybody happen to remember from last week what free fall gravity on Earth is? Yep, 9.8 or 10 meters per second squared. Oftentimes all around a 10 meters per second squared. AP will take either one, right? So let's go about that, okay? Right. Let's set up same 3 sets of axes that we did earlier in class for the car. Going at constant velocity, only this one is not a constant velocity situation, right? Okay. This ball is going to be speeding up as it's falling. Now let's do distance in meters versus time in seconds. Let's do velocity in meters per second versus time in seconds. Let's do acceleration meters per second squared versus time in seconds, right? So same 3 sets of axes as before, but we got a new story. So these graphs are going to look different. We're going to take a quick, whoa. Okay, we're getting short on time. I'm so sorry. I would really like to walk around the room and find some winners, but I'm just got to walk you guys through this, okay? Right. Let's start with the middle graph. Okay. V versus T. Okay. Guys, do you think that's going to look a lot like this? No, if you drop the ball, guys, the word drop tells you what about initial velocity? There you go. V naught is 0 meters per second, right? After that, isn't it just G times T? Right? And what's that graph shape? Straight line, zoop. Okay. I like to start with the middle graph and then branch out from there. You guys remember that? Okay. It's just like that, isn't it? Is that? Okay. Now, what's the slope of this line again? Yeah, G, which is 10 meters per second squared about, right? Which tells you what about the coordinate of the acceleration versus time? It's constant. In this case, we'll just call it an even, well, G or 10 meters per second squared, right? Okay. Now, and if you want to add up the area underneath that now rectangle, it gets you back to here. Okay. How about X versus T? What Here, you guys know V naught 0. You guys just told me that. So can you just boil it down to this? X is 1/2 AT squared. Because what shape is that? Starts with a P. Parabola? Is that just like your guys' car incline lab? X versus T started out looking like a parabola shape, didn't it? Right? So after 1 second, maybe it's fallen 5 meters, but after 2 seconds, now it's up to like 20 meters. Right? Right. Okay, you guys good there? Okay. By the way, this whole like relationship of like instantaneous rates of change is the slope, take you from top to bottom. And if you accumulate the area underneath, they'll take you from bottom to top. These three graphs are connected, right? You guys know that's a calculus relationship? You guys don't know? Right? So if you're taking calculus, guys, what's the rate of change called in calculus? Starts with a D. Like a derivative. Right? You guys wouldn't get there yet. That's right, right? And as you go from here to here, maybe just be like next semester, that's called integration, right? So here we go. Let me flip my screen here. Give you guys where's my screen flipper? Here we go. Okay. There's a video I want to play with you guys. Here we go. Call time. What's the answer? Right, right. All right, just in time. That's your distance is 1/2 AT squared. Right, you guys have a great afternoon. I'll see you tomorrow. Hopefully Wednesday. Time will tell.